everybody. We are OboeBass. My name is Carrie and I play the oboe.
And my name is Rolf and I play the bass.
We play a lot of programs and we go to a lot of different schools, probably just like yours, and we have many different programs. We can't come to your school right now, so we're making a program right here in our living room in Minnesota so you can watch a program in your living room in South Dakota. Of all the programs we have, we chose this one to play for you today. It's called The Science of Music. Now, like scientists, we are going to do a few little experiments today, and we'd like to have you participate in some with us. So in order to do that, you're going to need 5 different items. So feel free to pause this recording at any time so you can run and get the items, or so you can write them down and then go and get them. But here's the list of 5 items. First, you need a pair of scissors. You also need a plastic straw. You need a glass bottle that's empty. You're also going to need some water to put in that glass bottle. I put my water in this green watering can, but you can use anything, a pitcher, a measuring cup, anything where you can pour out of it. The last thing you're going to need is a jump rope. If you don't have a jump rope, you can use a regular piece of rope. You can even use a Slinky if you have one of those.
Now, we know that you might have some questions as we're talking about all this science stuff, and we're sorry we can't be in your classroom or your living room to answer those questions personally. But if you just write them down in the comments underneath this video, we will answer them as quickly as we can, and hopefully that will help.
So this is called the science of music. We know you know what music is. You listen to music, you dance to music, maybe you play music, you love music. But there's a very important principle that maybe you already know that we want to make sure that everyone's aware of. And that principle is that all that music is sound. And sound is vibrations. Maybe you've learned this in your science class. Vibrations that travel through the air. And these vibrations travel like waves. So there are 3 important things we want you to know about music and sound. And the first is that sound travels in waves.
The second thing we want you to know is the size of things making the sounds makes a difference in what kind of sounds are made. For instance, things that are really big or really long make really low sounds like this.
And things that are really small or really short make high sounds like this.
The third thing we want you to remember about sound is that sound travels really, really fast. In the space of 1 second, sound travels 880 feet. That's 1/6 of a mile. And if you want to think of it another way, that is like the length of 3 football fields in the space of a second. You're going to run 3 football fields this fast. Here's the starting gun. Boom! You're done.
Wow, that is fast.
That's really fast. Now, when we talk about the science of music, we are going to talk about music the way scientists talk about things. And scientists look at the world a little differently than most people. They're very careful about what they see and how they describe it. So there are 3 main things we want you to remember about what scientists do. The first thing scientists do is they observe. They pay very close attention to what they're studying and try and notice everything about it. After they observe, the second thing they do is measure. They find some way to measure it so they can describe it to other scientists so it's very much easier to communicate when you're talking about the same way of measuring and observing things. After you make your measurements and your observations, the third thing scientists do is use those measurements and observations to make predictions about, well, what would happen if we did this? Or if we did that, what would be different about the result? So the three things are observe, measure, and predict.
Okay, scientists, I think you've probably observed something the whole time we've been having this program for you. And I think the thing you have been observing is right up here at the top of our screen. You see this green square with the squiggly line that keeps moving? That is called an oscilloscope. That is a scientific instrument that measures the waves as they travel through the air. And what's great about this oscilloscope is that it can freeze the waves so then we can look at it. Right now, I'm going to freeze the waves, and Rolf and I are just going to make a lot of noise so we can get all this going. Yeah, we can see what it looks like.
See what it looks like then.
All right, so what do you think, Rolf? How do we do here?
Pretty good.
Does that look good?
Yeah.
All right, so I'm going to bring across, I made a little chart for you, and I'm going to bring it in, and this chart shows us kind of on the top line when we make noise.
Show with the arrow.
Yeah.
They can see
I'll show you. Yeah. When we have noise, whoops. When we have noise, this is what happens. This is what it looks like in the waves. They're irregular. They're different sizes, kind of like what we have up here. But now I'm going to make a different sound. I'm going to whistle. So kind of will sound like a musical note. And then I'm going to freeze it and we can look at that. So when I whistle, and if you look at that, you see it looks way more regular. Look at that. Nice and beautiful. They're all the same size, kind of like what I wrote down here where it says tone. It kind of looks exactly the same. Now when we have the part that looks like tone where it's very regular, that's where science steps in, because then it's possible to measure how all these waves look and predict and observe and all the scientific things when we have something that's very regular. So now that we have that in mind, we're going to play another piece of music for you, and we're going to want you to watch the oscilloscope and observe what happens when we play different notes and different sounds. See if the oscilloscope can show you some things and see what kinds of observations you can make when we play our next piece. So I hope you noticed some very interesting things about the oscilloscope and the waves and how the sounds were making the waves do very interesting things, because we had a couple of very interesting sounds in that last piece. So now that we're scientists and we're observing and we're predicting and we're measuring, we also have some terms that we need to make sure that you know, and there are three that we really think are important for you in this topic here. The first one we want to talk about is wavelength. because we're going to be measuring the waves. So we have to know the length of the wave. It's very simple. And you can figure out, we would measure from the crest of one wave to the next, and by crest we mean the top. So if you look at this picture here, we have the top of this wave here, and we're going to measure to the next wave, the top of the next wave.
Let's measure those with the arrows and see if they can see how that all lines up.
Yeah, we have an arrow here. We can show you. We have the top of this wave here going to the top of that wave there. And that means in this whole picture, you can see we have 3 waves. 1 from here to here, number 2 from here to here, and number 3 from there to there. So we have the length of the wave, and that's important because we're going to measure. Now when we talk about the length, we also want to talk about how many we can fit into the space of 1 second, because that's usually how we measure how many waves we have. And so when we talk about that, the term we use for that is frequency. And that makes sense because frequency makes us think of frequent, or how many. And so we sometimes use the word hertz instead of frequency. So if someone says something is 200 hertz, they're meaning there are 200 waves per second that are going through the air. We like using the term frequency because it lets us know what the sound is like and what the note is. So if it's a high-pitched note, that means it's a very high frequency. There are a lot of waves going through the air. And if it's a low-pitched note, it's a low frequency. Very few waves are traveling through the air. So what we're going to do, in fact, here is a picture. Oops, here's a picture of there's a picture of a low note. You see it's a long wave and it has a low frequency because there's only one wave there. What I'm going to do is I'm going to bring the oscilloscope down and make it a little larger so we can see it. I'm going to ask Rolf to play a note, and then I'm going to see if I can freeze that wave so we can really see what that note looks like. So Rolf, can you play a low note for us? Look, that wave. Let's look at that. It's a very, let's see. So here's the crest of that wave. It goes below the line here and it goes above the line there. It's kind of a sneaky wave. So there's a crest here and then there's another crest there. So in this whole picture, we have one wave. It has a low frequency. It's very long. That's what it sounds like.
Now Carrie is going to give us an example of a high frequency, high pitch note. So let's see if we can freeze the frame there and see what a high frequency note looks like. Could you play your high frequency note, Carrie? Wow, look at that. For the bass, it was only one wave for the whole picture, low frequency. For the oboe, look at all those waves. There are a lot of different waves. That's a high frequency note. We have one other measurement of sound waves we want to talk about, and that is amplitude. And amplitude measures how loud the sound is. And to get that amplitude, that is volume, high or low volume. And amplitude is kind of like the word amplifier. If it is really low amplitude, it's a quiet note. And if it's high amplitude, it's a loud note. So you see how we're measuring instead of the length of the waves like that way, or the frequency, we're measuring the height of the waves from top to bottom. So this is what a low amplitude soft note looks like. Let's see if Carrie can provide one and we'll take a picture. Carrie, could you play a really quiet, low amplitude note? All right, I think we captured it. So let's look at this picture. You see, in this picture, the waves are not very tall. That is very, very low amplitude. But we also see the other things going on. We see the length of each wave, and we can count the number. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 waves in this picture. Okay, now, Carrie, I'm going to ask you to play the exact same note and see what the wave looks like when you put a lot of amplitude, a lot of noise and sound. It's really loud. That is an excellent picture. Now you can see from this picture, the waves are very tall. That's a high amplitude, loud wave. And when we count them, we're going to see it's the same frequency and the same wavelength as the low note. The only thing that's different is the amplitude. So that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 waves.
Now we're going to do a little experiment, and we want you to get one of the items we asked you to have at the beginning of the program. And right now we're going to use the jump rope. Remember, if you don't have a jump rope, you can just get a regular rope. You can even use a Slinky. Sometimes a Slinky is pretty fun to use this way. And this is a way you can make your own wave live in your living room. So we're going to make a wave here. What are we going to try to show on this wave, Rolf?
Well, first let's show the amplitude. So let's use a really low amplitude wave. So you see, that wave is not very tall. So that would be a quiet note if it was a musical note. Let's make it a real high amplitude note. Now look how high the wave is. That is high amplitude. And the last thing we can do is we can change the frequency and the wavelength. So we're going to try and get a lot of really short waves. So look at how many waves there are and how short they are from top to each wave. So that's a high frequency note with short wavelengths.
Okay, we've learned all this stuff. Now we are going to have a test. So the test, what we're going to do is we're going to show you some pictures of some waves, and then it's your job to tell us two things. First, you're going to tell us if it's loud or soft, and then you're going to tell us if it's high-pitched or low-pitched. Here's our first slide. Okay, so we have, is this a loud note or a soft note? So if we look at the amplitude, it's very high amplitude, so that means it's a loud note. Now we need to know if it's a low note or a high note, so we look at the frequency. It looks like it's a low frequency, which means there's a long wavelength, so that means it's a very low pitched note. That is a low, loud note. Look at the next one. Okay, so is it loud or soft? Let's look at the amplitude. It's a low amplitude. That means it's a quiet note. Let's look at the frequency. We have a lot of waves, and they're short wavelengths, so that means it's a high-pitched note. Next one. You're good at this. What do you think? Is this a loud or soft note? That is a soft note because it is a low amplitude. Look at that. And if we have a pitch, is it going to be a high or low pitch? We look to the frequency. Looks like it's a low frequency with a long wavelength. That is a low pitched note.
And very quiet.
Here's our last one. That's a loud note. That's right. Because look at that amplitude. It's very high. And what about the pitch of that note? Is it high or low? It is a high frequency. Yep. So it is a very high pitched note. Good. You did very well on this test. Okay, we're going to bring back our oscilloscope, and then we are going to play another piece of music for you. I think this is going to be a pretty familiar piece of music. I think you've heard this before, but we want you to watch the oscilloscope because it's always interesting to see what that shows while we play the notes, especially if it's a familiar piece of music for you.
Now that you know some facts and some terms about science, I want to show you how you can apply those to the bass. Now, the bass is a member of the string family, and that means what makes the vibration on string instruments is the actual strings of the instrument. If you look very closely here, when I pluck the strings, you can see how the string vibrates. It gets kind of fuzzy looking. And that is the vibration that makes the sound wave that we hear as music. Now the bass is really big, so it makes really low notes. And so right now, I want you to just kind of observe what happens. When we play the notes, there are two main ways we make the strings vibrate. One is by plucking them with our fingers like this, and that's called pizzicato. The other way we make sound is with this thing. This is called a bow. And this kind of looks like white tape here, but it's really hundreds of strings that are put really close together. I don't know if you can see that. And those strings are made from horse hairs. They're hairs from the tail of the horse, and that's because science has not found anything that works better than horse hairs to make string instruments vibrate. If you look at a human hair under a microscope, it's very smooth, almost like a fish line. But if you look at one of these horse hairs under a microscope, it looks really rough and bumpy. So it really grabs the strings and makes them vibrate. And you can also hold the notes a little longer with this. When you do pizzicato, the note kind of dies away pretty quickly. But with the bow, you can keep pumping energy into the sound to make it keep vibrating. So that's how we make the strings vibrate. But you've noticed another thing while we've been playing. We play a lot of different notes. The way you change notes on a string instrument is by putting your fingers on the string like this. Now the way that works science-wise goes back to one of the very first things we told you in the program. Remember, long things make really low notes and short things make really high notes. So when I play a really low note on the bass string, if I don't put any fingers down at all, the vibration of the string goes way from the top here, way down to this white piece of wood that's called the bridge. So this whole length is vibrating. Now if I change the length of the string that is vibrating, I do that by putting my finger down on this bass. So if I just play the string without any fingers, it sounds like this, because this length is vibrating. If I put a finger down, it sounds higher, because there's a shorter length of string that's actually vibrating. You can actually see this up close. We're going to bring the camera up close so you can see what's vibrating. So, when I put my finger on the string, it's not going to vibrate between my finger and the top of the bass, but it's going to vibrate from here way down to the bridge. So watch what happens, how the bow makes the string vibrate. See how fuzzy that looks? Now if you go up to where my finger is, on the other side of my finger, the string is not vibrating. So the way I've changed the notes is by changing the length of string that's actually vibrating. So that gives you some observation, so you kind of understand the general principle of how we change notes on a string instrument. But besides using observations, we can use actual measurements. So Carrie, could you help me measure the length of the string? I'm going to hold one end of the tape measure up at the very top of the bass, and Carrie's going to hold one end of it right on the bridge. So how long is that? Let's measure that. Get it really tight. Okay, how long is that?
42 inches.
Okay, that's 42 inches. So when I get this whole string vibrating, I get that note. Now, you know in music, sometimes people with very low voices, like your dad maybe, can sing a note that's the same as your mom sings higher. So daddy might sing like this, and mom sings the same note. So that's something we call an octave. Now, are going to measure where that next octave comes. So first we measured the sound that you get from a 42-inch length of this string vibrating. Now we're going to measure what the next octave is. So Carrie is going to match this note, and I'm going to slide up until the note matches again. See how that matches again? Now we are going to measure the length from where I'm stopping the string vibrate. So now the string is only vibrating between my finger and the bridge. So let's see what that length is. What do we got?
21 inches.
Now do some quick math. How is 21 related to 42? That's right, it's half. So 42 divided by 2 is 21, and we get the octave. That's kind of interesting. I'm going to make a guess that this pattern continues. And this guess is, like we say in science, it's a prediction. I'm going to predict if instead of having 21 inches of string vibrating, we have half that much vibrating, we'll get to the next octave. So what's half of 21? That's right, 10 and a half. So Carrie, if you could just measure where 10 and a half is without even playing the note, she's going to point where I should put my finger. So where is it? Right about there? Okay, there. Okay, now she's going to play the note, and let's see if the note matches. Yep, it's the same note again. So, my next prediction is that if I'm just going to guess, I'm going to do about half that length, and I bet we'll get another octave. Yep, so that's how we change notes on string instruments, by changing the length of the string that's vibrating.
I am now going to talk about the science involved with playing the oboe. For all oboe players, the most important part of the oboe is right here. That's the reed. The reed is the part that makes the vibrations when we start to play the oboe. This reed, you can see, is very, very small and hard for you to see. So I am going to show you something else. I brought my big reed today so you can see the difference. Much easier to see the reed in the big reed. The most important thing for you to know about the reed is that it actually has two pieces of wood here that are tied together with this string, and they make a hole in the middle of it. See that hole? That's what we blow into, and once the air hits that, both pieces of wood start vibrating and making the sound on the oboe. We oboe players make our reeds, and so today you're gonna practice making an oboe reed of your own with materials you have at home. And here's where we need some of those other items we talked about. So you will need for this to have two items. You will need the plastic straw and the scissors. So if you need to pause this to go get them, now's your time. So with the plastic straw and the scissors, we're going to make an oboe reed. Now, I know you're all familiar with straws, and you know a straw has a big circle opening, and we have to get it kind of flat because it has to look like the reed opening, which is kind of flat. So what we're going to do is we're going to fold it, crease it, squeeze it really hard with our fingers so it makes a crease. And once I feel like I've folded it and I've made the crease there, that's when I'm going to take my scissors. I'm going to stick the scissors inside the straw, and I'm just going to snip it just up about a ½ inch. It doesn't have to be exactly a ½ inch, but you can measure like your fingernail or just the first segment of your finger, and that should be about the right size. So I'm going to snip up about ½ inch, and then I'm going to flip it around so that the other side I can snip on that crease like that. Now remember, we have to get this to look flat like the way this reed looks here. So the only way to do that with a straw, or this is the best way, is to do this. I don't really like to do this, but my daughter does, and she showed me how. I think some of you probably like to do this too. So now, once you do this, and it's always an experiment because you have to make sure it works. And you have to try. Sometimes you have to put more of it in your mouth, sometimes put less of it in your mouth, sometimes blow harder, sometimes don't blow as hard. And I always have to experiment too because I never know exactly if this is going to work. So here we go now. I'm going to blow on this and see how it works. I'm kind of blowing like so now you've made a reed. But we can go even further than that because remember we said the length determines what the note is that you play, and that if it's a longer length, it's a lower note. If it's a shorter length, it's a higher pitch note. So Rolf is going to help me. He's going to take the scissors and cut it shorter while I play. Oh, there they are. And when you do this, you must be very careful. Okay, tell your parents or have your parents help you, and someone can cut the straw and someone else can hold it and blow. If you are cutting the straw, make sure you're looking only cutting the straw, not anyone's fingers. And if you are blowing, make sure your fingers are curled in so they cannot get cut. Okay, so here we go. See if you can hear if the notes change while we blow. Did you hear it get shorter? And now we have another oboe reed too. So you can have that reed also you can play on. So now that is exactly how the oboe works. The reed makes the sound and we blow into the oboe and we get the initial sound. But it's the fingers that may have us change the notes. If you look carefully on this metal stuff, you can see that these are the ones that have circles on them, and that's where I put my fingers. When I put my fingers down, it changes the length of the oboe because there are holes under all of these metal things, and when I put these down, the holes make the oboe that long. So when I put more fingers down, the notes get lower. And that's how it works. Now we can do another experiment that also shows this even better. And that is where we need our last two items. And you can pause the tape and go get your glass bottle and your water. So with your glass bottle and your water, we can demonstrate why the oboe works the way it does. And the way it works is by getting a column of air that vibrates. And this is the best way to show this to you. We love blowing in bottles, don't we? It's one of my favorite things to do. And you just blow across this and you make a sound. In fact, if you like to do this, you should play the flute because flute players blow across a hole and it makes a sound. Now, when you blow across it, when the air hits the other side of the hole, it makes a sound and it makes the whole air, the air inside of the bottle starts vibrating, and we call that a vibrating column of air. So the whole bottle inside is vibrating. I'm going to have us look on the oscilloscope what this sound looks like on the bottle. Look at that. It looks like we have about, I don't know, 2 waves. How many waves does it look like we have here?
2 bumps anyway.
2 bumps. Let's see. We have, whoops, whoa. We have 1 here and 1 here. See, 1, 2. Okay? So now we're going to do our experiment. I'm going to pour water in here about
Oh wait,
halfway
before you
full.
do that, let's check what the note is.
Okay, we got that? Now I'm going to pour water in here, and I'm going to do it about halfway full. It doesn't matter at all. It doesn't matter exactly, but you can see I have maybe a little more than halfway full. Okay, doesn't have to be exact. So now our prediction is what? When we blew in here the first time, the whole column of air is vibrating because it was air from here to here. And now we've changed it so the air is now a lot shorter. So we have a shorter column of air. It's smaller. So what do you think is going to happen when that vibrating column of air sounds? I have my prediction. Do you have yours, Rolf?
Yep.
Here it is.
Should we start with the first note we had and see if this is higher or lower?
Sure. In fact, we can see if it is higher, it should have a higher frequency. We should have more waves, right? Here we had 2 waves on our first note. Look at that. What did we have? Now we have 3 waves on this note. It's a higher frequency. It's a higher pitched note because the column of air that's vibrating is a shorter column of air. I want to tell you one more thing about the oboe because it has a lot of very interesting facts. And one interesting fact about the oboe is that the oboe is the instrument that tunes the orchestra. And by tuning the orchestra, I mean it will play one note and every other member of the orchestra has to match that note to sound just like that so that all the instruments sound the same and the orchestra sounds the best it can sound. And the oboe has that job. So when the oboe tunes the orchestra, it plays a note, and this is the note that it plays. And that's called an A. And that A, if we had our oscilloscope, freeze it, our oscilloscope would show, here I'll play it and you can watch the oscilloscope. And when we have that note, there are 440 waves per second whenever that note is played. Now we're going to try to see what that means because that is a lot of waves per second. You have a machine that gives us seconds, right, Rolf?
Yep,
Let's hear
1
it.
click per second.
Okay, so those are seconds. I think we can all clap. Let's all clap 1 second, 1 per second with our ticker. Okay, that's easy. How about if we clap 2 per second, like this? Clap with me. Okay, how about 4 per second? Okay, you ready? How about 440 claps per second? Can you do it? Oh, you can't do it. It's so fast. Can you imagine? 440 per second vibrations are going into your ear when you hear this note. That is a lot of waves for our ear to listen to.
Okay, now based on what you already know, you can figure out some more stuff. Carrie just told you that the frequency of that note was 440 vibrations per second. Using that information, plus how fast sound travels, you can figure out how long each of those wavelengths were that were coming in 440 times per second. And if you remember, I said sound travels really fast. 880 feet in the space of 1 second. So if you can imagine a really long wavelength, if it was just a frequency of 1 in that 880 feet, you would have a wave that was 880 feet long. So let's imagine another wave for the sake of argument. Let's say that this wave we're talking about, that there were 2 waves in those 880 feet. So you divide 880 by 2 and you get 440 feet long waves. So each of those waves would be 440 feet long if the frequency was 2. Now we decided that the frequency was 440. So what happens when you divide 880 by 440? Well, you kind of just flip the equation around. 880 divided by 2 is 440. 880 divided by 440 is 2. So each of those wave lengths is 2 feet long. So just so you can imagine this, when Carrie plays that note, I'm going to pretend that I can grab one of the waves out of thin air. Let's hear the note. I got a wave. And these waves are each about 2 feet long. So when Carrie plays that 440 frequency note, that means that 440 waves 2 feet long are going into your ear every single second. There are some other practical things you can also use with what you've learned about waves and the speed of sound. For instance, if you're ever out in a thunderstorm, you can actually figure out how far lightning is by how long it takes for the sound of the thunder to reach you. Remember, we said sound travels 880 feet per second. That's about 1/6 of a mile. So that means it takes 6 seconds for sound to travel 1 mile. So if you see a lightning strike over there and you count to 6, that means that that lightning was 1 mile away. If you count 3 seconds between when you see the lightning and you hear the thunder, that means the lightning was only half a mile away. If you see the lightning and you hear the thunder 1 second later, that means it's time to go inside because that lightning hit only 880 feet away and it's getting closer.
One other thing that I think is very interesting when we're talking about waves and hearing and how different creatures hear these waves is to look at the numbers of this. So let's start with us, with humans. The lowest number of waves that a human can hear is 20 waves per second. Think of the lowest note you can possibly think of. That's like 20 waves per second. And if we think about the highest note that we can hear, think about the highest whistle possible, the highest note, the highest tone you can hear, 20,000 waves per second, 20,000 hertz is what a human being can hear. Okay, that seems like a lot. 20,000 vibrations per second is a lot of vibrations. But let's think about dogs. You know how dogs, they say, can hear higher notes than humans? And have you ever heard of a dog whistle? They have these whistles that when you blow them, you go, and it sounds like nothing. We can't even hear it to us. It sounds like nothing. But dogs, when you play it, they go crazy because it's super duper high and they have hearing that can hear that. So humans, the highest note they can hear is 20,000 hertz. What do you think for a dog it is? For a dog, the highest note they can hear is 60,000 hertz. But then let's go to another animal, a bat. You know how they talk about bats use vibrations to fly around, and they call it sonar. And they'll make a sound, and the sound waves travel around, and then they can tell where everything is by how the sound travels. So they have super sensitive hearing. A dog, highest was 60,000 hertz. A bat, the highest they can hear, guess what it is? 150 1,000 hertz. That is extremely high. We can't even imagine that. Now we're going to go to the other end. I don't know how familiar you are with mice, but sometimes you can walk behind a mouse and they don't even move. It's like you think, what, can't they hear me? And it's true, they can't hear you. Let's go back to that note that we said for the A, that the oboe plays for the orchestra. That's 440 hertz. That's this. That just sounds like a normal note to us. But to a mouse, that sounds like lower than the lowest note we could possibly hear. In fact, they can't even hear that. That is too low for a mouse to hear. So I could play that for a mouse and they wouldn't even run because they wouldn't even know I was playing a note. In fact, this note which is a pretty high note, that is the lowest note that a mouse can hear. And that's about 1,000 hertz here on this end. That is the lowest sound they can hear, the note I just played. So if you just played regular music for them, low notes, they wouldn't hear. They wouldn't run away from you because they couldn't even hear it. So I think that's very interesting to see how the science plays into what we can hear, how we can hear it, how we can count the vibrations, and all of these observing and predicting and measuring ideas we talked about in this program. We have one final piece we want to play for you. And we want you to just see if you can think of all these things, the amplitude, the frequency, the wavelengths, all these ideas, and watch our oscilloscope for one final time for the last piece that we're going to play. So thanks for watching our program today. We hope we can see you in a future date at your school doing our programs of music for you.
Thanks for letting us play for you.
Bye-bye.
Bye.